So this video is about Archimedean property and their problems. So this is one of the interesting property which we use for the convergence and all. So if this property is simple, that is we are taking two positive real numbers, then they are saying that then there exists a natural number n such that ny is greater than x. So if you are taking two positive numbers, then we can say we can give the this what we can say inequal strictly greater than. So we can make one strictly greater than the other by giving some natural number. So this n will always exist. That is the guarantee it is giving. So this is the Archimedean property. Let's prove this one. Let's discuss the Archimedean property of real number. So that it states that if x and y are belongs to real number, that is x is positive, y is positive, so they are fixed, then there exists n in n such that ny is greater than x or nh is greater than y, something. Okay, so the theorem statement is obviously trivial. So you have two positive real numbers. So you can say one is greater than the other, strictly greater than the other, by multiplying some n. So this is one of the major property that we use for proving the convergence. Let me write the proof hint. Okay, firstly I'm writing the hint. So first is method of contradiction. I'm proving by method of contradiction. So that is I'm going to take ny is lesser than x for all n, or we can, if you want to change also we can change, because here ny there exists n. So we can change this n to be k in order to not to confuse between this n and this k, because you are going to say here for all k in n. So ky is lesser than x for all k. So here y and h are fixed, right? So it means the, by varying this k, you can see this is a sequence. Okay, so you can say this is a sequence where k belongs to natural number. So this is one of the sequence you are getting. You can name it as yes. So here it acts as an upper bound for this sequence. Okay, this is a sequence. Next hint will be, next clue will be supremum property or completeness property of real number. So by this property an LUB exists. Okay, I'll say what is the completeness property. So LUB will obviously exist for this sequence, and which we denoted by B. So what I'm going to do is, the next hint is like py will be lesser than b. This is by LUB property, and which is again lesser than p plus 1 times y, which means it is a contradiction, because this is not an LUB. It becomes a contradiction to our assumption. Hence we can prove this theorem. So let us discuss the proof. Okay, I'll go with a step by step. Suppose there does not exist n in n such that ny is greater than x. Suppose that does not exist. Now I'm going to say this statement is same as for all k is a natural number, ky is less than or equal to x. So that is my contradicting statement is this one. So this leads to conclusion that x is an upper bound of the sequence. My sequence is nothing but ky, varying this k. So this is the sequence. It is bounded by some element x, because x is fixed. So this is what I have done so far. Now I can do what I have to do. I don't want upper bound, I want least upper bound. So I can use the completeness property of R. Completeness property of R. It states that, so this statement is like every non-empty set of real numbers which is bounded above, right? Or we can say that has has an upper bound will also has the supremum inside the arch. That is what the completeness property states. This is also called as supremum property. Okay, so now we can write by this property, by this supremum property, I am having a p in real number such that my s, that is ky, okay, my s is nothing but ky, is less than or equal to b. So this is what the supremum property says, and this b acts as an LUB, okay, least upper bound. So now I am going to say this is not the least upper bound, there is something else also there. Like that I have to contradict. Okay, so without loss of generality or anything, we can say b minus y is lesser than b. This is trivial, so we don't want to write this also, but because by hypothesis y is greater than 0, which is given. Okay, this one we have to write it in a bracket, like since y is greater than 0, minus y is lesser than b. So now I am going to say as there exists a natural number p, let's say p, which belongs to a natural number, which is going to be such that it will be lies in between these things, it's lesser than p. So this is, I'm just saying this is a trivial case, and I'm going to insert one of the element from the sequence so that it will be holds, it will obviously holds. Okay, so I'm going to say this implies p plus 1 times y is greater than b. Okay, I missed this one because it can be b also. Okay, so b minus y is obviously less than b minus y is obviously less than b because y is strictly greater than 0, so b minus y is lesser than b. So this is okay, but I'm going to insert one element which can be equal to b also, so we have to do it in this way. So p plus 1 times y, which is greater than b, that is, it implies p plus 1 times y is greater than b. I can say py is a member of S only. So no, like this I can say p belongs to n, p plus 1 also belongs to natural number only. This implies p plus 1 times y belongs to S, because in the set S all the elements will be of this form. So p plus 1 times y belongs to S. So this statement says that b is lesser than p plus 1 times y. B is the least upper bound. That means the sequence S is equal to, I have contradicted, that's all, the proof over, but I'm just saying p ky such that k belongs to natural number. This is my set, and which is bounded by, I mean least upper bound is b. So for any member of the sequence from the set, it will be all bounded by this element. So there should not be any one element which is like there should not be existing any element such that this should not happen for our case. But here we have got at this point, and hence this contradicts our assumption, and hence the proof over here. Okay, so this contradicts, and hence we have proved. So how we have done a contradiction? Because the sequence S is equal to ky, we can say it as a sequence or set, it is not a matter, because this is a real sequence, because the value, the output is a real number. So this sequence has an least upper bound as b, but there exists some element in this sequence which is not like this actually, which becomes like this, but it should be lesser than, but it becomes greater than. So this means it is a contradiction, because everything should be lesser than b, because b is the least upper bound. So this is the contradiction, and hence we have proved that ny is greater than x.